There is something peculiar about the universe. The more carefully we look at it, the more clearly we see that the things we do not understand vastly outnumber the things we do. The entire history of physics and astronomy is a story of resolving one mystery only to discover three more beneath it. Every answered question reveals a deeper question. Every instrument built to look further into the cosmos reveals structures and phenomena that no one expected and no one can fully explain. Tonight, that is not a source of anxiety, it is a source of peace. The mysteries of space are not problems demanding your immediate attention. They are the background condition of the universe, the deep and patient unknowns that have existed for billions of years before you were born and will continue to exist long after. They are the universe's way of remaining interesting, and on a quiet, dark night, the best response to them is exactly what you are doing, lying still, breathing slowly, and letting the darkness hold them. Here are the most extraordinary unsolved mysteries of space. They are offered not as puzzles to solve, but as meditations to rest inside. Each one is a door that no one has yet been able to open, a question so fundamental that the greatest minds in the history of science have stood before it and been humbled. You are in good company in not knowing the answers. No one does. The first mystery is dark matter. Approximately 27% of the energy content of the universe consists of something called dark matter, a substance or collection of substances that exerts gravitational force on ordinary matter but does not interact with light in any detectable way. It is neither luminous nor opaque. It neither emits, reflects, nor absorbs electromagnetic radiation of any wavelength. It passes through ordinary matter without interaction. Its existence is inferred entirely from its gravitational effects. The evidence for dark matter is overwhelming and has been accumulating since the 1930s, when the Swiss astronomer Fritz Zwicky noticed that the galaxies in the Coma cluster were moving too fast. The total mass of the cluster's visible stars and gas was insufficient by a factor of hundreds to produce the gravitational field needed to keep the cluster from flying apart. Either the laws of gravity were wrong, or there was much more mass in the cluster than could be seen. Zwicky called this missing mass Dunkel Materie, dark matter, a term that persisted. In the 1970s, the American astronomer Vera Rubin and her collaborator Kent Ford measured the rotation curves of spiral galaxies, the velocities at which stars at different distances from the galactic center orbit. Under the laws of gravity, stars far from the center of a galaxy should orbit more slowly than stars close to the center, just as outer planets in the solar system orbit more slowly than inner planets. But Rubin and Ford found that the rotation curves of spiral galaxies are flat. Stars at the outermost reaches of the disk orbit at the same velocity as stars near the center. The only way to account for this is to surround each galaxy in an enormous halo of invisible mass, a dark matter halo extending far beyond the visible disk, providing the additional gravitational pull needed to explain the observed velocities. The Bullet Cluster, a pair of colliding galaxy clusters about 3.8 billion light-years away, provides perhaps the most direct evidence for dark matter. When two clusters collide, the gas clouds of each cluster interact electromagnetically and are slowed by the collision lagging behind. The dark matter, which does not interact electromagnetically, passes through the collision unimpeded, like two clouds of smoke. Observations of the bullet cluster using gravitational lensing, which maps the total mass distribution by measuring how the cluster's gravity bends the light of background galaxies, show that most of the mass of the cluster is now displaced from the location of the gas, centered instead on the colliding halos. The mass is separated from the gas. This is precisely what dark matter would do. Despite all this evidence, no one has ever directly detected a dark matter particle. The leading candidate for decades has been the WIMP, the weakly interacting massive particle, a hypothetical particle with a mass somewhere between 10 and 10,000 times the mass of a proton that interacts with ordinary matter only through the weak nuclear force and gravity. Enormous detectors filled with ultra-pure liquid xenon and located deep underground, shielded from cosmic rays, have been searching for the rare interaction of a WIMP with a xenon nucleus. The LUX Zeppelin detector at the Sanford Underground Research Facility in South Dakota, the current generation's most sensitive such detector, has ruled out vast regions of parameter space where WIMPs might exist. It has found nothing. The absence of a detection does not prove WIMPs don't exist, but the parameter space where they can still hide is shrinking. Other candidates include axions, an extremely light hypothetical particle proposed originally to solve a problem in quantum chromodynamics, and that would also make an excellent dark matter candidate. Axions would interact with photons in the presence of a strong magnetic field, and experiments such as the Axion Dark Matter experiment, ADMX, are searching for this interaction. So far, no axion has been detected. Dark matter is one of the deepest mysteries in physics. It is not that we have no idea what it might be. We have many ideas, and many of them are well motivated by particle physics theory. The mystery is that none of the leading candidates has been found, despite decades of sensitive searching. Dark matter may be a particle we have not yet imagined. It may be something even stranger. It may, in some models, be not a particle at all, but a modification of the laws of gravity. We do not know. Let your breathing slow. The second mystery is darker still: dark energy. In 1998, two teams of astronomers studying Type 1 supernovae, using the brightness of these stellar explosions as standard candles to measure distances across the universe, discovered that distant supernovae were dimmer than expected. They were farther away than they should have been if the universe were expanding at a constant rate. The only explanation was that the expansion of the universe was accelerating. Something was pushing space apart, working against gravity on the largest scales. This something was called dark energy, and it comprises approximately 68% of the total energy content of the universe, making it the dominant component of the cosmos. The simplest description of dark energy identifies it with Einstein's cosmological constant, a term he originally added to and then removed from his equations of general relativity. The cosmological constant, designated by the Greek letter lambda, represents a constant energy density of empty space. The vacuum itself has energy, and this vacuum energy drives the accelerating expansion. The problem is that when physicists calculate the expected energy density of the vacuum from quantum field theory, they get a number approximately 10 to the power of 120 times larger than the observed dark energy density. This is the largest discrepancy between theory and observation in the history of physics, a mismatch of 120 orders of magnitude. Some unknown mechanism cancels the enormous quantum vacuum energy down to the tiny observed value with a precision of 120 decimal places, and no one knows what that mechanism is. This is the cosmological constant problem, and it has been described as the worst prediction in the history of physics. The universe is 68% dark energy. We do not know what it is. We do not know why it has the value it has. We do not know whether it is truly constant or whether it varies slowly over time. We do not know whether it will always be with us or whether it will someday change, with potentially catastrophic consequences for the large-scale structure of the universe. The third mystery is the Hubble tension. The Hubble constant, designated H0, is the rate at which the universe is currently expanding, measured in kilometers per second per megaparsec. For every megaparsec of distance, space is expanding by 80 kilometers per second. There are two main methods of measuring H0. The first uses observations of the cosmic microwave background, fitting the observed pattern of temperature fluctuations to the standard cosmological model to infer the expansion rate in the early universe and project it forward. This method gives a Hubble constant of 67.4 kilometers per second per megaparsec. The second method uses the cosmic distance ladder, measuring distances to nearby galaxies using Cepheid variable stars and Type 1 supernovae, and observing their recession velocities directly. This method gives a Hubble constant of about 73 kilometers per second per megaparsec. The two measurements disagree by about 8%, which sounds small but corresponds to a statistical significance of 5 sigma. The probability that the disagreement is due to chance is about 1 in 3.5 million. Both methods have been checked and rechecked and cross-validated extensively. The disagreement is real. Either one or both methods contain unidentified systematic errors, or the standard model of cosmology, lambda CDM, is incomplete and needs to be revised. The James Webb Space Telescope has been used to remeasure the Hubble constant with independent data and has obtained a result closer to the higher value, but the tension has not been resolved. Some physicists believe the Hubble tension is the first crack in the standard cosmological model, a hint of new physics waiting to be discovered. No one knows. The fourth mystery is the Fermi Paradox. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos when a conversation about UFOs led him to ask a simple question given the vast number of stars in the galaxy, many of which are billions of years older than the Sun and could have given rise to civilizations far more advanced than ours. And given the enormous timescales available for such civilizations to expand and colonize the galaxy, where is everybody? The galaxy should, by simple statistical reasoning, be full of signs of technological civilizations. We see none. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicating civilizations in the Milky Way as a product of various factors: the rate of star formation, the fraction of stars with planets, the fraction of planets that develop life, the fraction of life-bearing planets that develop intelligence, the fraction of intelligent species that develop technology, and the longevity of such civilizations. The first several factors are now reasonably well constrained by observation. Star formation rates are known. The fraction of stars with planets is known to be high, and even the fraction of planets in the habitable zone is estimated from surveys like Kepler. But the biological and sociological factors remain entirely unknown, and they dominate the result. The Great Silence, the absence of any confirmed extraterrestrial signal, has been explained in many ways. The most disturbing is the Great Filter hypothesis, the idea that there is some step in the development of complex, intelligent, spacefaring life that is extraordinarily unlikely, a filter that almost no evolutionary lineage passes through. If the filter is behind us, then the evolution of intelligence on Earth somehow navigated an improbable bottleneck, and we may be among the very rare civilizations in the galaxy. If the filter is ahead of us, then the development of advanced technology reliably leads to extinction through war, environmental destruction, or some other mechanism, and the silence of the galaxy is the sound of civilizations that did not survive their own technological development. Other proposed explanations include the zoo hypothesis, the idea that advanced civilizations are aware of us but have chosen not to interfere, perhaps out of an ethical commitment equivalent to the prime directive of science fiction. There is the planetarium hypothesis, the idea that we are in a simulated environment where the apparent emptiness of the galaxy is a designed feature. There is simple distance. Even if the galaxy contains thousands of communicating civilizations, the distances between them are so vast that signals may be too faint to detect with current technology. There is time. Civilizations may rise and fall on timescales that make simultaneous overlap rare. We do not know. The fifth mystery is the fast radio burst. In 2007, astronomers combing through archival data from the Parkes Radio Telescope in Australia discovered a burst of radio emission so brief that it lasted only a few milliseconds and so energetic that it must have originated from an enormous distance, far outside the Milky Way. This was the first fast radio burst, FARB 010724, detected in data from 2001. Since then, hundreds of fast radio bursts have been detected, and some of them repeat. The same source produces multiple bursts over time. The first repeating source, FARB 11102A, was localized to a dwarf galaxy about 3 billion light-years away, and its radio pulses were found to be highly polarized and to rotate with an extraordinarily large rotation measure, suggesting they pass through an extremely strong magnetic field near the source. The leading candidate for the source of fast radio bursts is the magnetar, a neutron star with an extraordinarily powerful magnetic field, 10 to the power of 14 to 10 to the power of 15 Tesla, compared to the already enormous 10 to the power of 8 Tesla of an ordinary neutron star. In April 2020, an FARB-like burst was detected from a magnetar within our own Milky Way, SGR 1935 plus 2154, providing strong evidence that at least some fast radio bursts originate from magnetars. But the enormous energies of some extragalactic FRBs, the variety of their observed properties, and the existence of both repeating and apparently non-repeating sources suggest that there may be multiple types of sources, or that the phenomenon is more complex than a single magnetar explanation accounts for. The sixth mystery is the Great Attractor. For decades, astronomers mapping the large-scale structure of the universe noticed that the Milky Way, and indeed an entire region of the universe encompassing hundreds of galaxy clusters, is moving in the direction of the constellation Centaurus at a velocity of about 600 kilometers per second relative to the cosmic microwave background. This motion is far too large to be explained by the gravitational pull of any known nearby structure. The source of this flow was dubbed the Great Attractor, and it was located in a particularly unfortunate direction from our perspective, directly behind the densest band of the Milky Way in the zone of avoidance, where the dust and stars of our own galaxy's disk obscure our view of everything beyond. Subsequent observations in X-ray and radio wavelengths, which can penetrate the dust of the Milky Way's disk more effectively than optical light, have revealed that the Great Attractor region is associated with the Norma cluster, a massive galaxy cluster about 250 million light-years away. But even the Norma cluster is insufficient to account for the full motion of our region of the universe. The flow extends much further toward a region called the Shapley supercluster, about 650 million light-years away, which is one of the most massive concentrations of mass in the observable universe. And even beyond the Shapley supercluster, the picture remains uncertain. The Laniatea supercluster, the enormous structure of which the Milky Way is a part, is itself streaming toward a convergence basin that may extend to scales not yet fully mapped. The seventh mystery is the cold spot. The cosmic microwave background, the afterglow radiation of the Big Bang, is extraordinarily uniform across the sky, varying in temperature by only about 1 part in 100,000. These tiny temperature variations are the imprints of quantum fluctuations in the early universe that seeded the formation of all large-scale structure. The pattern of these fluctuations is described well by the standard cosmological model, with one exception: a region of sky in the constellation Eridanus, about 5 degrees in diameter, is anomalously cold, about 70 microkelvin colder than expected given the predictions of the standard model. This is the CMB cold spot. Several explanations have been proposed. The most mundane is a statistical fluctuation. The cold spot is unusual, but not definitively impossible given the known physics of the early universe. The most intriguing is a supervoid, a large underdense region of space, roughly 1 billion light-years across and several billion light-years away, that would cause photons passing through it to be cooled slightly as they climb out of the void's shallow gravitational potential well. Observations do suggest the presence of a supervoid in the direction of the cold spot, but whether it is large enough and deep enough to fully explain the anomaly is debated. The most exotic explanation is a bubble collision. If the universe underwent a period of cosmic inflation that produced a multiverse, other bubble universes might have collided with ours in the very early universe, leaving an imprint on the CMB. The cold spot has been proposed as evidence of such a collision. This hypothesis is unproven and perhaps unprovable. We do not know. The eighth mystery is the WOW signal. On August 15th, 1977, a radio telescope at the Big Ear Observatory at Ohio State University detected a narrowband radio signal at a frequency of 1,420 megahertz, the frequency of neutral hydrogen emission, and the frequency long considered the most likely candidate for an intentional interstellar signal because of its fundamental nature. The signal lasted 72 seconds, the full duration of the telescope's field of view, and was so strong that the astronomer who noticed it in the printout, Jerry Amon, circled it and wrote "Wow" in the margin, giving the signal its name, the WOW. Signal has never been detected again, despite repeated targeted searches of the sky region from which it appeared to come. It bore all the hallmarks of an artificial interstellar signal. It was at the expected frequency, it was narrowband, and it rose and fell in intensity exactly as a signal from a specific sky location would as the telescope's beam swept past. No natural phenomenon has been convincingly identified that could produce the signal. One hypothesis proposed in 2017 is that the signal was produced by a comet, either 266P Christensen or P2008Y2, which were in the general vicinity of the sky region at the time and would produce hydrogen emission. This hypothesis is contested. The WOW signal remains unexplained. Whether it was a natural but unknown phenomenon, a technical artifact, or something else entirely, we do not know. Let your body be completely still. The ninth mystery is the ultra-high-energy cosmic ray. Cosmic rays are charged particles, mostly protons and atomic nuclei, that travel through the universe at extraordinary speeds and bombard Earth's upper atmosphere continuously, producing cascades of secondary particles detectable by experiments on the ground. Most cosmic rays have energies well within the range explained by known astrophysical processes, supernova shock waves, and other violent phenomena. But some cosmic rays have been detected with energies above 10 to the power of 20 electron volts, energies so high that they approach the G-SC limit. The decay limit, named after Greisen, Zatsepin, and Kuzmin, who predicted it in 1966, is the theoretical maximum energy at which a proton can travel through the universe. At energies above the decay limit, protons interact with the photons of the cosmic microwave background radiation, losing energy in the interaction. This means that any proton with energy above the GK limit must have traveled no more than about 160 million light-years to reach us. Otherwise, it would have lost too much energy and CMB interactions to still be above the limit. The puzzle is that some of the highest energy cosmic rays that have been detected have no obvious sources within 160 million light-years in the direction they came from. Either they did come from a very powerful nearby source that we have not identified, or something is wrong with our understanding of ultra-high energy particle physics, or the particles are not protons but some other type of particle whose interactions with the CMB are different. The origin of ultra-high energy cosmic rays remains one of the most baffling unsolved problems in high-energy astrophysics. The 10th mystery is the information paradox. When something falls into a black hole, does the information about its quantum state survive? In quantum mechanics, information is conserved. The laws of physics that govern quantum systems are time reversible, and the quantum information contained in any physical system is never destroyed. But Stephen Hawking showed in the 1970s that black holes evaporate through a process of quantum mechanical radiation, now called Hawking radiation, which is perfectly thermal, it carries no information about what fell into the black hole. If a black hole completely evaporates and only thermal Hawking radiation remains, the information about the original quantum states of everything that fell in has been destroyed. This contradicts quantum mechanics. This is the black hole information paradox, and it has occupied physicists for nearly 50 years. Various proposed resolutions include the possibility that information is somehow encoded in the Hawking radiation through subtle quantum correlations, the possibility that information is stored in a Planck scale remnant left behind when the black hole evaporates, and the possibility that the black hole creates a new region of space, a baby universe that contains the information. The most recent and mathematically sophisticated approach involves the concept of the page curve and the island formula, derived from insights in holography and quantum gravity, which suggests that information does escape in the Hawking radiation through subtle non-local correlations that only become apparent after the black hole has evaporated past the page time, roughly the midpoint of its evaporation. The island formula appears to give the right answer for the entropy of the Hawking radiation, suggesting that information is preserved, but the physical mechanism by which information escapes remains deeply unclear. The 11th mystery is the fine-tuning of the constants of nature. The universe we inhabit is governed by a set of fundamental constants: the speed of light, the gravitational constant, the charge of the electron, the masses of the quarks and leptons, and others. The values of these constants are not predicted by any current theory. They are measured experimentally and inserted into the equations of physics by hand. And yet, when one examines how sensitive the properties of the universe are to small changes in these constants, it turns out that many of them are finely tuned to values that allow complex structures like stars, planets, and life to exist. Small changes in the strength of gravity or in the ratio of the electromagnetic force to the strong nuclear force, or in the mass of the electron, would produce a universe in which stars cannot form, or in which atoms are unstable, or in which the universe collapses or expands so rapidly that structure never emerges. The most famous example is the cosmological constant. If it were slightly larger, the universe would have expanded too rapidly for galaxies to form. If it were slightly smaller and negative, the universe would have recollapsed before stars could ignite. The observed value of the cosmological constant is about 10 to the power of 120 times smaller than the theoretical expectation, and yet it is just large enough to be causing the current accelerating expansion, just small enough to have allowed structure to form. Proposed explanations include the anthropic principle and a multiverse containing many regions with different values of the constants. Only regions with values compatible with complex structures will be observed by conscious beings, because only in such regions do conscious beings exist. This is logically sound but scientifically unsatisfying to many physicists, because it does not predict or explain, it merely accounts for. The 12th mystery is Oumuamua. In October 2017, the Pan-STARRS telescope in Hawaii detected a small object moving through the inner solar system on a hyperbolic trajectory, an orbit that was not bound to the sun and that indicated the object had come from outside the solar system. This was the first interstellar object ever detected passing through our solar system, and it was designated 1I 2017 U1 and given the name Oumuamua, a Hawaiian word meaning roughly first distant messenger. Initial observations suggested it was roughly cigar-shaped, perhaps 400 meters long and 40 meters wide, tumbling as it moved and darker than expected. The deeply puzzling aspect of Oumuamua was its acceleration. As it moved away from the sun, Oumuamua was accelerating more than gravity could account for. Other solar system objects show non-gravitational acceleration from the outgassing of volatile materials when heated by the sun, but no outgassing from Oumuamua was ever detected. A paper by astrophysicists Abraham Loeb and Shmuel Bialy proposed that Oumuamua's properties were consistent with a light sail, a thin, highly reflective sheet propelled by the pressure of sunlight, possibly of artificial origin. This proposal attracted enormous attention and equal amounts of skepticism. Other proposed explanations include a hydrogen iceberg, a fragment of solid molecular hydrogen from a dense interstellar cloud that would outgas invisibly in solar radiation, a nitrogen iceberg, a sliver of nitrogen ice from the surface of a Pluto-like body in another planetary system, and a fractal dust aggregate, a loosely bound fluffy object with an extraordinarily high surface-to-mass ratio. None of these explanations is fully satisfying. Oumuamua has now left the solar system and cannot be studied further. Its nature remains unknown. The 13th mystery is the Boötes Void. The large-scale structure of the universe consists of filaments and walls of galaxy clusters surrounding enormous voids where few or no galaxies exist. The Boötes Void, discovered in 1981 by Robert Kirshner and colleagues during a survey of galaxy redshifts, is one of the largest known voids in the observable universe, approximately 330 million light-years in diameter. Within this enormous volume of space, astronomers found only about 60 galaxies, where based on the surrounding density, they would have expected to find thousands. The void is not completely empty, but it is extraordinary underdense. If the entire Milky Way were placed in the center of the Boötes Void, our ancestors would not have been able to detect even the nearest galaxy to the Milky Way until the 20th century, because the nearest neighbor would have been hundreds of millions of light years away. The existence of the Boötes Void is not itself anomalous. Within the standard model of cosmology, voids of various sizes are expected features of the large-scale structure. But the Boötes Void is at the high end of what the standard model comfortably predicts, and its formation history and detailed properties have been subjects of ongoing study. The largest known structures in the universe, the filaments, walls, and voids of the cosmic web, are in principle limited in size by the scale of the universe itself, and objects approaching this limit challenge the standard cosmological assumption that the universe is homogeneous and isotropic on very large scales. The 14th mystery is the matter-antimatter asymmetry. The laws of physics, as best understood, treat matter and antimatter nearly symmetrically. For every process involving matter particles, there is a corresponding process involving antimatter particles. The Big Bang, which created the matter and energy of the universe from a state of extremely high density and temperature, should have produced equal amounts of matter and antimatter. If it did, the matter and antimatter would have annihilated each other completely, leaving a universe consisting only of radiation and no ordinary matter at all. But we exist. The universe contains vastly more matter than antimatter. The ratio of baryons, ordinary matter particles, to photons in the universe is about 1 in a billion. For every billion photons, there is 1 baryon. The billion minus 1 antimatter particles annihilated with a billion matter particles, leaving 1 surplus matter particle for every billion that annihilated, and from those 1 in a billion surplus particles, all the atoms in the universe, all the stars, all the planets, all the living things are made. The process by which this asymmetry was created is called baryogenesis, and it requires 3 conditions first identified by the Russian physicist Andrei Sakharov in 1967. Baryon number violation, which means processes that create more baryons than antibaryons. CP violation, which means the laws of physics treat matter and antimatter differently at some level, and departure from thermal equilibrium, which means the early universe must have been in a non-equilibrium state when baryogenesis occurred. All 3 Sakharov conditions can be satisfied in principle within the standard model of particle physics, but the amount of CP violation known to exist in the standard model is far too small to account for the observed baryon asymmetry by many orders of magnitude. New sources of CP violation beyond the standard model are required to explain why there is something rather than nothing. None has been discovered. The 15th mystery is the nature of time. Physics, at its most fundamental level, is time symmetric. The laws of quantum mechanics and general relativity are equally valid run forward or backward in time, and yet we experience time as asymmetric. The past is fixed and known, the future is open and unknown, and events always unfold in one direction. Heat flows from hot objects to cold objects, but not the reverse. An egg breaks but does not unbreak. Information is forgotten but not spontaneously remembered. The direction of time we experience, what physicists call the thermodynamic arrow of time, is a consequence of the second law of thermodynamics, entropy. The degree of disorder in a closed system always increases with time, and this defines what we call the future as the direction of increasing entropy. The mystery is not the second law itself, which can be derived from statistical mechanics and the enormous number of ways in which high entropy states can be realized compared to low entropy states. The mystery is the initial condition. Why was the entropy of the universe so extraordinarily low at the Big Bang? A random initial state of the universe would almost certainly have been in a high entropy configuration, and a high entropy universe has no arrow of time, everything is in equilibrium, nothing changes. The low entropy of the Big Bang is what made the arrow of time possible, and the existence of stars, planets, life, and everything that persists or evolves depends on the continuing flow of energy from low entropy sources like stars to high entropy sinks like the cold of space. But why the Big Bang started with such extraordinarily low entropy remains one of the most profound unsolved problems in all of physics. Let your thoughts drift and slow. These are the mysteries that the universe keeps. They are not withholding them from us out of cruelty. They simply have not yet yielded to the tools we have built to understand them. The 16th mystery is what is inside a neutron star. When a star between roughly 8 and 20 times the mass of the Sun exhausts its nuclear fuel and collapses, the collapsing core becomes a neutron star, an object typically about 20 kilometers in diameter, containing 1.4 to 2 solar masses of material compressed to a density exceeding that of atomic nuclei. The outer layers of a neutron star are a crystalline lattice of neutron-rich nuclei permeated by a superfluid of neutrons. But deeper inside, beyond a depth of about a kilometer, the density exceeds the density of ordinary atomic nuclei, and the matter is in a state that no laboratory on Earth can produce, and that quantum chromodynamics, the theory of the strong nuclear force, cannot yet reliably calculate. Theorists propose that the core of a neutron star may contain free quarks, or strange quark matter, in which strange quarks are present alongside up and down quarks, or even more exotic states of matter. The nicer instrument aboard the International Space Station has measured the radii of several neutron stars with sufficient precision to constrain the equation of state of dense matter, providing some evidence against the most extreme proposed states. But the deepest interior of a neutron star remains beyond both observation and reliable calculation. The 17th mystery is phosphine on Venus. In September 2020, astronomer Jane Greaves and colleagues announced the detection of phosphine gas in the atmosphere of Venus using the James Clerk Maxwell Telescope in Hawaii and the ALMA interferometer in Chile. Phosphine is a molecule of one phosphorus atom and 3 hydrogen atoms, and on Earth it is produced almost exclusively by biological organisms or by industrial processes. Its presence in the Venus atmosphere at concentrations of about 20 parts per billion was extraordinary. The atmosphere of Venus is highly oxidizing, and phosphine should be rapidly destroyed by the Venusian conditions unless it is being continuously replenished. The announcement sparked an enormous scientific controversy. Subsequent reanalysis of the data reduced the apparent phosphine abundance significantly, and the detection was contested by multiple groups. Independent searches for phosphine in Venus's atmosphere produced conflicting results. Whether phosphine is genuinely present in the Venus atmosphere, at what concentration, and what its source might be, remain matters of active scientific debate. If phosphine is present, and of biological origin, it would be the first evidence of life beyond Earth. If it is absent, or of abiotic origin, it would be a lesson in the difficulty of remote detection of trace atmospheric constituents. The 18th mystery is quantum gravity. General relativity, Einstein's theory of gravity, published in 1915, describes the universe at large scales with extraordinary accuracy. Quantum mechanics describes the universe at small scales with equally extraordinary accuracy. The two theories are, between them, the most precisely tested theories in the history of physics, but they are incompatible. General relativity is a classical theory. It describes the curvature of space-time as a smooth, continuous field that can in principle be specified with arbitrary precision. Quantum mechanics is a quantum theory. It describes the world in terms of probability amplitudes, discrete quanta, and the fundamental uncertainty of the Heisenberg principle. When one attempts to combine the two, to quantize gravity in the same way that the electromagnetic force was quantized to produce quantum electrodynamics, the calculations produce infinities that cannot be removed by the standard methods of renormalization used in other quantum field theories. The Planck scale, the scale of energy and length, at which quantum gravitational effects become important, is approximately 10 to the power of -35 meters in length and 10 to the power of 19 billion electron volts in energy. These scales are so far beyond any current or foreseeable experimental reach that testing a quantum gravity theory directly is essentially impossible with current technology. Two main approaches to quantum gravity have been developed. Loop quantum gravity proposes that space-time itself is quantized at the Planck scale, consisting of discrete units of area and volume connected in a network called a spin foam. String theory proposes that all fundamental particles are different vibrational modes of one-dimensional objects called strings, and that gravity is the result of a closed string mode called the graviton. Both approaches have mathematical consistency, but have not made contact with experiment in a decisive way. The reconciliation of general relativity and quantum mechanics remains perhaps the deepest open problem in fundamental physics. The 19th mystery is why there is something rather than nothing. Gottfried Leibniz, the 17th century German philosopher and mathematician, posed what he called the fundamental question of metaphysics. Why is there something rather than nothing? Why does anything exist at all? For most of human history, this question was considered the province of philosophy or theology. Quantum cosmology, developed in the 1980s by physicists including Stephen Hawking and James Hartle, has attempted to address it scientifically. The Hartle-Hawking no-boundary proposal suggests that the universe has no initial boundary in time, that the concept of a moment before the Big Bang is as meaningless as the concept of north of the North Pole, and that the universe emerged from a quantum state describable by a path integral over compact, closed geometries with no edge. In this picture, the universe does not need a cause because it has no beginning. Time itself emerges as a property of the quantum state. This is a beautiful and mathematically elegant framework, but whether it is correct is unknown. Whether it even constitutes an answer to Leibniz's question, rather than a reframing of it, is itself a matter of philosophical debate. The 20th mystery is vacuum decay. The Higgs field, the quantum field associated with the Higgs boson, has a particular energy value in our current vacuum, called the vacuum expectation value of the Higgs field, that gives fundamental particles their masses. Calculations suggest that our current vacuum may be a false vacuum, a local minimum of the Higgs field's energy that is stable for now, but is not the lowest possible energy state. If the universe tunnels quantum mechanically to the true vacuum, the Higgs field value would change, and with it the masses of all fundamental particles, the strengths of all fundamental forces, and the chemistry of all atoms. The result would be the destruction of all organized structures in the universe, propagating outward from the point of nucleation at the speed of light, invisible until the boundary of the true vacuum bubble reaches you. Calculations using the known values of the Higgs boson mass and the top quark mass suggest that our vacuum is metastable. It will likely not decay on any cosmological timescale, but the probability is non-zero. Whether this is a genuine concern depends sensitively on the precise values of the fundamental parameters and on physics beyond the standard model that has not yet been measured. Every generation of physicists and astronomers has inherited a set of unsolved mysteries and has passed on a different, often smaller set. Some mysteries that seemed permanent have dissolved in the light of new understanding. The Pioneer anomaly, a small unexplained acceleration in the trajectories of the Pioneer 10 and 11 spacecraft noticed in the 1990s and for years suspected of pointing to new physics, was eventually explained in 2012 by the anisotropic thermal radiation from the spacecraft's own nuclear power source, a genuine mystery studied for 2 decades, resolved by patient investigation into the mundane reality of heat. This happens in science. What appears mysterious at one level of understanding becomes ordinary at the next. It is one of the most hopeful patterns in the history of knowledge. But not all mysteries resolve so cleanly. Dark matter has been known for 90 years. The cosmological constant problem has been known for 50. The information paradox has been known for 45. The Fermi Paradox has been known for 75 years, and the universe remains, as far as we can tell, silent. Some mysteries are genuinely deep, touching something fundamental about the nature of reality that our current conceptual frameworks are not yet equipped to reach. These mysteries do not resolve, they wait, patient and enormous, for a conceptual revolution that may or may not come within any given human lifetime. There is a kind of peace available in the awareness that the universe is larger and stranger than understanding, not the peace of giving up, but the peace of appropriate scale, the recognition that your particular anxieties and concerns, whatever they are, exist at a scale enormously smaller than the scale of the mysteries that occupy the finest minds that have ever lived. Dark matter and dark energy and the information paradox and the arrow of time have not been solved by anyone. They are simply here, steady and patient and vast, waiting for whatever understanding might eventually come. The 21st mystery is the giant arc. In 2021, astronomer Alexia Lopez announced the discovery of a structure she called the giant arc, a curved arrangement of galaxies, galaxy clusters, and quasars stretching approximately 3 billion light-years across the sky, located at a redshift of about 0.8, corresponding to a distance of roughly 9.2 billion light-years. If confirmed, the giant arc would be one of the largest structures ever discovered in the universe. The cosmological principle, a foundational assumption of the standard model of cosmology, states that the universe is homogeneous and isotropic on sufficiently large scales. It should look the same in all directions and from all locations, with no structures larger than a certain scale. The theoretical maximum for coherent cosmic structures in the standard model is typically placed at about 1.2 billion light-years. The giant arc, at 3 billion light-years, would significantly exceed this limit, potentially challenging the cosmological principle itself. The discovery has not yet been independently confirmed as a physically coherent structure rather than a chance alignment, and the debate about its significance is ongoing. The 22nd mystery is the flatness problem. The geometry of the universe, the way in which space is curved on the largest scales, is determined by the total energy density of the universe relative to a critical density. If the density equals the critical density exactly, space is flat, and the three angles of a triangle drawn on the largest scales add up to 180 degrees. If the density exceeds the critical density, space is positively curved like the surface of a sphere and will eventually recollapse. If the density is less than the critical density, space is negatively curved like a saddle surface and will expand forever. Observations of the cosmic microwave background and the large-scale structure of the universe show that the geometry of the universe is extraordinarily close to flat, with the total density within about 0.4% of the critical density. This is remarkable because, in the standard Big Bang model without inflation, the flatness of the universe is an unstable equilibrium. Any deviation from exact flatness in the early universe grows with time, and a universe that is close to flat today must have been extraordinarily close to flat at the time of the Big Bang, to 1 part in 10 to the power of 60. Why the universe started with this incredibly precise value of the density is the flatness problem. Cosmic inflation, the hypothetical period of extremely rapid expansion in the very early universe, resolves the flatness problem by stretching any curvature to unobservable scales. But inflation is itself not yet directly confirmed by observation. The 23rd mystery, perhaps the strangest of all, is the mystery of mathematics. The universe appears to be governed by mathematical laws. The laws of physics are written in mathematical language, from the differential equations of general relativity to the algebra of quantum mechanics to the group theory of the standard model of particle physics. Mathematics, developed by human minds working in abstraction, turns out to describe the physical universe with extraordinary precision. As the physicist Eugene Wigner wrote in 1960, the unreasonable effectiveness of mathematics and the natural sciences is a mystery. There is no obvious reason why the abstract structures invented by mathematicians for purely aesthetic or logical reasons should turn out to be exactly the structures needed to describe physical reality. Is mathematics discovered, existing independently of human minds, or is it invented, a product of the peculiar cognitive structures of human intelligence? And if mathematics is discovered, in what sense does it exist? Where is it? These questions lie at the intersection of physics, mathematics, and philosophy, and they have not been resolved. We do not know why the universe is mathematical, and we do not know whether it had to be. Tonight, the mysteries are keeping themselves. The Boötes Void is as empty as it was yesterday, and will be tomorrow. But wow. Signal has been silent for nearly half a century. The dark matter is passing through you right now, through the mattress beneath you, through the floor, through the bedrock, through the mantle of the earth, and out the other side, without interacting with any of it, as it has done every moment of your life, and as it will do long after you are gone. Somewhere in the universe, a magnetar is producing an ferb that will reach Earth's radio telescopes in a few billion years. Somewhere, the Higgs field sits at its current value, stable for now, holding the masses of all particles at the values that allow atoms and stars and you. Somewhere, The great attractor is slowly drawing everything in its direction as it has been for billions of years. You are lying in the dark. The universe is doing what it does. The mysteries are holding themselves, patient and enormous, and entirely unconcerned with whether they are ever solved. They have been here for 13.8 billion years. They will be here tomorrow. What you do not need to know tonight, what dark matter is, what dark energy is, whether the Fermi Paradox has a resolution, whether Oumuamua was a light sail, whether the universe is fine-tuned, or whether it is one of many in a multiverse where all possible values of the constants are realized somewhere, whether there is something rather than nothing for a reason. What you do need to know tonight, you are in the dark. The universe is around you, the mysteries are keeping themselves, and you are allowed to sleep. The universe has been here for 13.8 billion years. It was here for 4 billion years before the first single-celled life appeared on Earth. It was here for 8 billion years before complex multicellular animals evolved. It was here for 13.799 billion years before the question of what dark matter is was first asked by a human mind. The questions are new. The universe is old. Its mysteries are not urgent. They are patient. And in their patience, they offer a kind of permission, the permission to rest without understanding everything, to sleep without having resolved the deepest nature of reality, to be here for this night, in this darkness, without answers. Good night. Sleep in the mystery.